All right, I'm going to start a little bit early, just because I did have some questions on the homework. Yeah, just be careful with this. Questions on the homework assignment, specifically how to find the equation of a sphere when you're given how to find the center and radius of a sphere when you're given a form that is not so easy to work with. Completing the square, right? So, where are we? 10-1. So I thought I would do one that is a little bit different than the homework assignment. So something like 3x squared plus 3y squared plus 3z squared equals 10 plus 6y plus 12z. All right, so the instructions here on this section were to find the center of the sphere and find the radius of the sphere given this equation. So remember that the goal is to get it to look like this: x minus h squared plus y minus k squared plus z minus l squared equals r squared. All right? So did we talk about this last time? Equation of a sphere? Okay, this is it right here. Every x, y, and z that you can find that would satisfy this equation. So someone would have to tell you what h, k, and l are. So if those were constants, h, k, l, and r, then any x, y, z that you could find that satisfies the equation would basically lie on the surface of that sphere. So here we're asked to find the center and the radius. So we have to get it to look like this standard form first. And in the standard form you have x along with a number, that quantity is being squared, same thing with the y and the z. Here we do have x squared, we do have y squared, we do have z squared, but we also have some other variable terms on the other side. So what we're going to do is let's move all our variables to the left and all constants to the right. And I'm trying to group them up here. I don't have any x's over here. I'm going to bring this 6y over. I started early if you're coming in, don't worry. I won't normally start early. I'm just going over a homework problem, or a problem like a homework problem. Let's see, I get everything here? Let's see, 3x, 3y squared minus 6. Okay, everything there? All right, so I've moved variables to the left, constant to the right, and now to get this to happen, we have to use completing of the square, which is something that I was going over that in my pre-calc class the other day, completing the square. So it's something that I know you've seen in the past. Is there a question? No?
You can just divide by 3.
Yeah, so that is a good question. Can we divide by 3? And the answer is yes. All right, we can divide out of 3, but I'm not going to divide out of 3 because I just want to work with it as it is, all right, just to see what happens, all right? Okay, first thing I'm going to do is look at this right here. And I do not have any other x's, do I? No. So this is already kind of like this, except that what would the h be? What does it look like it would be? 0, right? So x minus 0 squared is the same as x squared. So this looks like I'm okay. These two, though, do not look like this. So I'm going to complete the square there. So remind me, what the steps are for completing the square. So,
You divide by 2.
so I'm gonna write it down over here, and I'm gonna write the whole thing down. This right here I want to complete the square on.
So
Got to have a factor out of a 3 first, okay? So instead of dividing out 3, as was suggested earlier, right, Eric? I'm just going to leave the 3 there, but I'm going to factor it out. Now, the reason you have to factor it out is because to do completing of the square, you must have a coefficient of 1 on your squared term, or your squared variable. So I have a 1 here now, right? The 3 is just going to come along for the ride. What's the next thing? Okay, so you look at the coefficient of the y term, -2, and you divide it by 2, always, right? You always divide it by 2, and that will give you -1, okay? Then you take that and you square it. That's the method for completing the square. All right. Does this ring a bell? Now this is where things are going to be different for each of you. What do you do next?
Plus 1 minus 1 minus 1.
Add it on both sides, or I heard
Plus 1 minus
+1 -1.
That is 0.
So I recommend that you do the +1 -1. And the reason why is because this 3 might mess you up. And actually in Cal 2, there were times where you had to complete the square and you didn't have an equation where you couldn't add things to both sides. So what I recommend is that you realize that right here next to this 2y is really a +0. And I'm about to insert that 0 using this number. So I'm going to go 3 y squared minus 2y. Here comes the 0, +1 -1. All right? That's still the same? Now, these 3 terms are guaranteed, the first 3, right, are guaranteed to be a perfect square trinomial, which will factor out to be y minus 1, that quantity squared. So I'm going to rewrite this, 3. Still have that 3 there, right?
Yep.
Okay, but these 3 become y minus 1 quantity squared. And I still have -1 here, close the parentheses. Now you can pass the 3 back through. Okay, so when I pass the 3 through, the 3 is going to just hop out in front of this parenthesis, and then the 3 is going to come out here and become a -3. Okay, so let me rewrite this. I've got 3x squared. This right here becomes 3y minus 1 squared, and then I still have -3. Y'all agree?
Yes, sir.
Questions? Okay, and now, you sure there's no questions?
So +1 minus 1 is for every time, no matter what stat comes out.
Well, it's plus whatever minus whatever. It's 1 because of this. So if this had been 3, we do +3 minus 3. And you always put it, make sure you put it right here inside. Don't put it outside the parenthesis, because then it's going to be incorrect.
Be sure to put the +1 first.
Yes, and it's this number right here, right? This will always be a positive number, right? Because it comes from squaring something. So you're always going to do the positive of that first, then minus. Okay, so now I need to do the same exact thing, but I need to do it on this piece right here. So I'm going to work a lot faster on this one. Ready? Okay, pull out my 3. 4z, right, like that. I'm going to take -4, take half of it, that's -2. I'm going to take -2 and I'm going to square it, that's going to give me 4. I'm going to add and subtract 4 inside the parentheses here. 3z squared minus 4z plus 4 minus 4. I'm going to now do my perfect square. Z minus 2 squared minus 4. And then I'll distribute through and I'll put it over there. All right, so I have plus 3z minus 2 squared minus what? 12. And then equals 10. So remember, I had to pass the 3 back through. That's why I got that -12. That's why I think there's a danger when you say, some students say, okay, I'm going to get this 4, I'm going to add it on both sides. Because that 3 messes things up. And if you do that, you actually needed to add a 12 to the other side, not a 4. And that, I think, just gets messy. All right, so I think we're there. All of our constants can come to the other side. So take those to the other side. When we move those over, what will we get?
25 on the right.
We get 25. So 25 on this side. And then all of these that are still here, this, and this, I actually do not want the 3 because in the standard form, there in front of these parentheses is a 1, right? So I'm going to divide through both sides by 3. So when I do that, I should get x squared plus y minus 1 squared plus z minus 2 squared. And then this is going to be over 3, right? So can you tell from that what the center is and what the radius is? Yes? Okay, let's see. The center is 0, 1, 2, and then the radius 5 over root 3. You're just taking the square root of top and bottom. And it's acceptable to leave it like that. I know some of you have been taught to never leave it like that. It's fine. Nothing wrong with that. All right. So I just wanted to show you at least one problem where I completed the square. We're going to move into 10.2 today, and hopefully get to 10.3 also.
I have a question.
Yes. Uh-oh. Did I erase what you had a question?
No, it's all right.
Okay.
In the last problem of the homework, the equation was x squared plus z squared is less than or equal to 9.
Uh-huh.
Does that mean, like, since there's no y, does that mean that, like, the axis of the cylinder is in the y-axis and is determined by a number that we don't know? But it's
Yeah. Okay. So it was what? It was x squared plus z squared is less than or equal to 9?
Isn't y free though?
Yeah, so in this case, because y does not appear, y can be anything. So think about it this way. If you have your x, y, z axes, and let's do it this way. X, y, z, make sure we have the right-hand rule there. And if you're looking at x and z as being the only variables in here, then that means you're focusing all your attention on the xz plane. So the xz plane is this wall right here, which in our classroom is that wall, isn't it? Okay, so you have something that lives on the xz plane, and it looks like a circle, doesn't it? Like if this was x squared plus, if it was x squared plus y squared equals 9, that would be a circle, standard circle. But it's x squared plus z squared. So it's a circle in the xz plane. Okay, so up against that wall in the xz plane, it's a circle, but it's also everything inside of that, and it has a radius of 3, right? It's everything inside of that. So it's like a disk now.
yeah, I thought it was a solid circle on the xz plane, but in the answer it says that it's a cylinder.
Yes, so that's where we are so far, right? That's what it would look like if I plotted all the points that satisfied this, right? And with the condition that y is equal to 0, right? Because if y is equal to 0, aren't you flattened out onto that wall?
Yeah.
But since y doesn't appear here, y could also be 1, right? All your y coordinates could be 1, which would just take this circle and draw it out a little bit further this way. So you'd have another circle out here. Or it could be -1, right? Or anything. So what you wind up getting is a solid bar tube, right? A solid bar that goes in both directions forever, right? This keeps going, and this keeps going. It's infinite. Yeah, so it's just a circle. Imagine taking a circle and just moving it back and forth forever in each direction, and you just get this solid bar. Make sense? What if this was, instead of this, it was equals?
Then it'd be a circle.
It would be hollow inside, right? So it would be like a tube.
Like a lot?
Well, this is more like a rod to me, right? Because rods are usually solid. Yeah, I don't know. Whatever. This is solid. With the inequality, it's solid. With strict equality, it's hollow on the inside. All right. Let's talk about vectors. I know that many of you have had vectors already or seen them. So maybe not. I don't know. How many of you have not seen vectors ever? Okay. All right. Good. You haven't been poisoned yet, yes. Okay, so vectors. Let me zoom in a little bit here. I brought a better mouse today. All right, so vectors. Vectors are, there's a lot of different definitions for vectors. I'm going to stick with this one. Vectors are objects. Has anyone here taken linear algebra or maybe taking it now? Okay. How many of you have taken it? Taken it? Okay. So in linear algebra, you may have learned that functions can be vectors. So in our world right now, we're going to look at vectors as being like this arrow thing. But in more general terms, it can be a lot more than that. So I'm going to say they're objects that have two properties. They have some sort of magnitude, a way of measuring a length. And you can measure lengths of functions. That's why I'm saying vectors can be functions, because you can measure lengths of functions. But again, that's beyond the scope of this class. It's just anything that has a magnitude in some way of obtaining some direction. Okay? And that's it. That's what a vector is. You've got to have magnitude and direction. Now, other words for magnitude are length or norm. And so you'll hear me use those words. They all mean the same thing. So the easiest way to visualize a vector is just to picture an arrow, right, that has some length to it, and then it's pointed in some direction. And this is a vector in two-dimensional space. And I can change, where this thing points, how long it is, right? These are all different vectors here.
Are the ends just called start and end points?
We're getting to that. Yep. Okay, in three-dimensional space, this is a little harder to see, but yeah, that's hard to see. So let me show you a vector in three-dimensional space. There you go. Okay? And, let's say the arrow is like this, all right? So there's a vector, there's a vector, there's a vector. Vectors in four-dimensional space? Sure, you can have that. We can't visualize it, but they exist. Okay, so some language when it comes to vectors. Where was it? I don't see it. There it is. Okay. So when it comes to vectors, we use a special notation to let people know we're talking about vectors. In most textbooks, they use a bold letter, like a bold V for vectors. But it's hard on a board, on a whiteboard, for me to draw in bold, right? So we also use this notation with this little half arrow on top. And that lets you know I'm talking about a vector. So here's why this is important. If I write x down, most of the time in your mathematical career, when we have talked about x, we've normally thought of x as being some real number, right? X is a number. Whereas if I write x now with this, that's no longer a number, it is now a vector. And there's a big difference between a number and a vector. All right? So just be aware of that. This vector is known as a displacement vector. So if you just have vectors sitting out here in space, that's called a displacement vector. Now the end that does not have the arrow, okay, is called the tail or the initial point. And the other end with the arrow is called the tip or the terminal point. So initial, this is where it starts, points out into this direction, terminates at this point. So you can actually look at it as a vector that does connect from one point to another point, right? From an ordered pair to another ordered pair, there is a vector between there, isn't there? But the vector itself is not an ordered pair, and it is not a line, right? Lines would extend in every direction, or in both directions forever. It's also not a line segment, because line segments don't have a concept of direction. Here, the arrow gives us direction. Understand? Okay, that's just some language. All right, this is important. Two vectors are said to be equivalent or equal if they have the same magnitude and the same direction. Position does not matter. And this is why vectors are so important to us in physics and engineering, because it gives us a way to quantify something where position is not as important as the length and the direction. So I'll give you some sort of example as to why that would be important. If I'm going to take this chair right here, right, and I'm going to grab onto it, and I'm going to start pulling it across the room, right, like this, I'm applying a force to this chair, right? And as I apply that force, I can imagine that the force I'm applying, you know, if I pull it real slow, like this, is different than the force if I pull it like this, right? And so how can we visualize that force? We can visualize it in the direction my arm is pointed is where I'm pulling, right? And then how hard I'm pulling is the force. So maybe we could represent that with, like, if I pull real slow, then the vector is really small, pointed in the direction of my arm, right? But if I pull really fast and hard, then it's the same direction, but it's more force, right? And as I move, this vector stays the same, doesn't it? I mean, I'm moving it around, but it's still the same force. Make sense? That's why it's important to understand that vectors are equivalent. They're always equal to each other, regardless of position. They just have to have the same magnitude and the same length for us to be able to say they're the same. So if we look at two vectors here, right, those are the same vectors. If I move one up and down, does not matter. As long as they have the same direction, pointed in the same direction, and as long as they maintain the same length, then you can't tell one from the other. They're exactly the same.
As long as you're parallel?
That's a great question. As long as they're parallel, no. Because the definition of parallel is you're about to get it, it's not what you would think. It's a little bit weird. All right? Okay, any questions on that? So be sure that if somebody gives you 2 points and says, draw the vector that goes from this point to this point, and you draw it, right? And they give you another 2 points and ask you to draw the vector between those two, then these two vectors, as long as this length and this length are the same and they're pointed in the same direction, they are the same vectors, right? All right.
What do you mean pointing in the same direction? Do you mean like?
I didn't put the arrow there. I should have. Huh?
Well, if they're given a degree,
Yes, like some
they have to be like the same.
pointed in the same direction. If we use two-dimensional space here, then we could say that if you extend from the initial point or initial the tail, right, and you imagine an angle here, and this angle would have to be the same, right? Okay. The problem is when you get to 3D, that's not as easy. Because when you're in 3D, like, you know, what direction am I pointed in? Like, where's your reference? We have to agree upon a reference. Well, the x-axis and maybe, you know, the y-axis we can get. Imagine if I'm gonna be looking here, pointing at the camera, then if this is my x-axis, I have a certain angle here and a certain angle there, right? So there might be still a way to understand direction that way. But I'm just saying 3D is a little more complicated than it is with 2D. All right. All right, so how do we find a vector? How do we actually find a vector if somebody gives us 2 points? Well, it's a very simple computation. Okay, so if somebody gives you an ordered pair, so this is a point A, which is x1, y1, they give you another point B, x2, y2, then the vector connecting from A to B is written this way, AB with the arrow on top, and then notice our use of angled brackets. We always use angled brackets when we're talking about vectors. Instead of parentheses, we use parentheses for ordered pairs, which are points, right? So you notice that up here, these are parentheses, and these are parentheses. So these are 2 points, and the result of going from A to B is a vector, so we use the angled brackets. And all you have to do is subtract the x-coordinates and the y-coordinates to get your vector. The order in which you do it is important, though. You can't just arbitrarily choose. And I'm going to do this in an example. So we'll actually do this computation. Remember, all these notes are online, so I'm expecting that you're not going to just copy everything and it'll take you too long. All right, so the vector from A to B would be a vector that goes from here to here. So the arrow would be up here, this would be your tip, and this would be your tail, right? That is not the same, right? It is not the same as that vector that goes from B to A. Why are they not the same? They're not pointing the same direction. Do they have the same length? Yes, okay, but that doesn't matter. To be the same, they have to be pointing in the same direction. So the vector from A to B is not the same as the vector from B to A. In three-dimensional space, if you have an ordered triple and another point, an ordered triple, then it's the same exact thing. You just subtract the x coordinates and y coordinates and z coordinates. I think there's an example. Yeah, here we go. And I think before we do this one, let's do one a little easier. Let's go in R2. Find the vector in R2 from 1, -4 to -3, 5. I'll draw a picture, even though we don't need it. Was there a question? No? Okay. 1, -4 is about right here. And -3, 5 is about right there. And we're going from here to here, right? So I want to know, what is that vector? Written in its angle bracket form. So V, I'll call it V.
What is that vector? Like, you mean
Yeah.
its magnitude?
No, I want to know how to write that vector.
Oh.
So,
-4,9.
okay, so how are you doing that? You're doing -3 minus 1, right? You're not doing 1 minus -3. That would be incorrect. It's always the point you're going to. That coordinate goes first, and then you subtract where you came from. Do not forget that, because if you mess that up, everything is going to be wrong. All right, so I'm going to go -3. I'm going to subtract 1, and then 5 minus -4 will be 5 plus 4. So we should have -4, 9. Okay? -4, 9. Now check this out. Let's act like you're going to start at the origin. Just everyone go to the origin and just go to the point -4, 9. Okay, so where would that be? 2, 3. Here's -4, right? And then let's go up 1, 2, 3, 4, 5, 6, 7, 8, 9. Like that. Oh, I messed that up. What do you see here? They're equivalent. Those are the same things, aren't they? Those two vectors are the same because they have the same length and same direction. Remember, position doesn't matter, right? So when you get this result, -4, 9, this gives you like this reference vector that you could draw it from the origin and then move it around anywhere, right? All right, so how about the actual example? That's a 3D vector. The thing with that is it's a little harder to draw it. But let's just make sure you can get the correct order. So what about the vector from A to B here? That's what that means, right? A to B. So I'm going to do -2, take away 6, 8 minus -5, and then 10 minus 6. I'll let you finish that. The one from B to A is the other way around, right? So 6 minus -2, -5 minus 8, 6 minus 10. Now, these give you, I want you to see the answers because there's something somewhat interesting about the answers. I don't know if it's too interesting, but is that what you get? So really, what's the difference between these two?
Well, they're equal and opposite direction.
Yeah, there's equal. They're almost same except everything's negative, right? Like been switched by negative or multiplied by -1, right? Just change signs. So I wonder if you could. We haven't talked about multiplication yet with vectors, But I wonder if this is true. If it's even possible to talk about negatives of vectors. I wonder if that would be true. Would it make sense that that would be somewhat true?
Yeah.
Right, according to this? This turns out to be the case, but just, we haven't talked about what it means to multiply a vector by a number. We haven't discussed it. Well, it's about to happen, but kind of ahead of myself there. All right, we need some more notation, some more language. There is something called the zero vector. The zero vector does not have any sort of direction, nor does it have any length. But we have some concept of, or I guess a notation. If I write this versus this, these are not necessarily the same thing, all right? This is the number 0. This is the vector 0. And just to show you the difference, the 0 vector in two-dimensional space is the vector 0, 0. The vector 0 in three-dimensional space is the vector 0, 0, 0. All right? So you cannot say that the number 0 is equal to the vector 0. That's like comparing an orange to a cat. They're not the same species. You know what I'm saying?
So is it just a dot?
Is what a dot?
The zero vector?
I don't know. Does a dot have any length to it? I guess as long as we agree a dot doesn't have any length, then you could say that. Sure. Right? When we talk about points in space, those don't. When you talk about a line, right? Line might be easier. When you talk about a line doesn't have any width to it, right? Just like a point doesn't have any width to it.
Is it technically nothing?
But you have to be able to represent it with something, right? So you draw something.
Is it technically nothing even though it's not there?
It's there.
Is there?
It's there. Well, look, just think about the number 0 that you've been using your whole life, right? I mean, can you give me an example of 0? Like, here's 1 pen. Can you show me an example of 0 pens? I guess you could like not have it there, but then there's nothing, right? But you still understand what I mean by 0, right? Same thing here. I can't show you the 0 vector, but we all kind of understand it's there. Does that satisfy you? Okay.
Just kind of silly thought.
All right, more language here. All right, what we call the components of a vector? Components. So let me put a vector up here, and then let me put this here. All right, this is a vector. This is a point. Although there's some trouble in our numbers, the way we do things, right, in math, you could argue that I'm saying that this is the open interval from 2 to 3 on the number line, right? You could. That's just because we just don't. We have poor notation. In certain things, we have poor notation. But so we don't confuse ourselves. This is a point, unless I tell you otherwise, all right? So this is a point, this is a vector. They are not the same thing, right? We call this right here the x coordinate of the point, and we call this the y coordinate of the point. This we call the x component of the vector, and this the y component. So if you call that a component, that's incorrect because it's not a vector. If you call that a coordinate, that's incorrect because that's not a point. Understand? Was there a question, Eric?
So like that vector starts where at the origin, and then it goes 2 units to the right, and then
That would be one place you could have it. Yeah, the question is, where is this vector, right? So it would go 2 to the right and up 3. That's what the vector looks like, but I could reposition it somewhere else and it would be the same vector. But if you needed to see it, that's what it looks like, all right?
So without A and B being specified, then you have no idea where it starts?
It doesn't matter where it starts.
It's just,
Doesn't matter where it starts. It's the position within your space is irrelevant. I know it's confusing because you want it to be somewhere. You want it to be locked in. You want to be able to see it, just like a line or something. We can visualize it, but we don't want to lock it down, okay? And the reason we don't want to lock it down is because a lot of times in the real world, when we're talking about quantities, those quantities can be changing as we move, or they can be constant. Like as we walk around, there's gravity, right? That force is always there. And so where is it pointed? It's pointed in direction, right? And so we don't want to have a different, I guess, how do I say this? We don't want to constantly have to worry about if we change position, then all of a sudden we have to redefine gravity. Like it's always going to be there. So a vector is perfect for it because the vector can move and it's still equivalent to itself.
As long as it's pointing in the same direction, it doesn't matter, right?
That's right.
It doesn't matter like, where you move, it's still pointing.
Pointed in the same direction. Yeah. Now, I mean, we could argue that, you know, if you change your elevation and, yeah, I get it, but just like, you know, right? It's conceptual. All right. All right, so we have x and y components for a two-dimensional vector. We have x, y, and z components for three-dimensional vectors. And in general, we use this notation right here. Instead of using like x, y, we use v1, v2. When I say v1, v2, I really mean v sub 1, v subscript 1, v sub 2, but I just say v1, v2. Is that all right with you? Three-dimensional, v1, v2, v3. All right, now that we got some of that language out of the way, all right, we have this very, very nice law called the Parallelogram Law. And if you've worked with vectors in the past, I'm sure you've seen this. It gives us a way of geometrically understanding what happens when you add two vectors together. If you take two vectors and add them, what happens? So here are two vectors. If we add them, yeah, that's how, you're asking how do we do it mechanically? Let's first look at it visually. So if I take this vector here, let's see, if I add the two together, if I take the vector u and I add the vector v, I get a resulting vector u plus v. And let's try and see what's happening here. If I take the vector u and I add v, look at it almost like a path. You start here at the tail of u, all right? The tail of u. You follow the tail of u up to the tip of u. You connect v, the tail of v, to the tip of u. And then follow v, and this is where you wind up. That makes sense? You go u, attach the tail and tip together, and go here. The result is that you really just went from here to here, right?
Yeah, that's your displacement. It doesn't matter.
That's what we call the resultant vector. All right? That's your resultant.
Which direction?
Pardon?
How do we know which direction it's
Because we started at u, so you start here, right, and you end here, so your direction is pointed this way. Make sense? Remember, it doesn't matter where I position u and v. As long as I attach the tip of u to the tail of v, or you could say it the other way, the tail of v to the tip of u. Now I have a question for you. Would this change if I did it the other way? Would I get a different result? What does your gut tell you? Has addition, in our number system, has addition ever has the order ever mattered in addition? No. It never has, right? Hopefully this will follow the same thing. Let me see if I can convince you one way or the other.
Doesn't it just change the direction? It's the same
Oh
vector.
no, because it's still the same vector, just like up there.
Let's do this. We're going to take v, right? And we're going to attach the tip of v to the tail of u. So I need to move this u around, don't I? Let me move this u around. I don't know if I'm going to be able to do this. Okay, there we go. I can't move it down anymore. So how about I move v up? Is that all right? Okay, there we go. Now they're attached. Yes? So I'm going to go starting here, right? The tail of v, follow down. There's the tip of u, takes me back up there. So the result is that I went from here to here, isn't it? Are they the same?
Yes.
Yes, because those two resultant vectors, the resultant vector means the vector that you get as a result of the addition. This black one here and this black one here have the same length, and they're pointed in the same direction, aren't they? Now, what I'm going to do, just so you can see why they call this the parallelogram law. Oh, that's not the one I want. I leave this one in red. Wow, that's a terrible red. And this one in blue, like this. And then let me move those back where they were. Man, it's not going to work. I'm a little offset because I didn't move things properly, but imagine if we just shifted this down a little bit. Can you all see? Can you all see this? Can you all see that? That's the parallelogram rule. Basically says that no matter how you do the addition, right? Doesn't matter which way you do it. You can do u plus v or v plus u. It creates a parallelogram, and these two resultant vectors are equivalent. So that's why they call it the parallelogram law. All right. See if I missed anything there. All right. That works in three-dimensional space also. Okay, on this one, I drew some vectors here, and I wanted us to try and figure out what those things are. So I'm going to try and make this a little bit bigger, see if I can fit this all on here. All right. If I was going to do v plus u, then I'm going to leave v where it is, right? And what am I going to do with u?
Take the tail of u and
Get the tail of u and attach it to the tip of v. So let's say that this is u right here. Okay, do you all agree it's about that long?
Yes.
So all I need to do is slide it, and I need to make sure I maintain its direction. Slide it and then just kind of bring it down, something like that. Y'all with me? Yes? So it's going to go up to about right there. Right? And so our answer is this vector. That right there is v plus u. Isn't it? The green one. So you start out here, you went v, then u, and the resultant is this. How about u plus w? Same idea, right? I'm going to take this w. It's about that long. I'm going to just kind of move it up, move it over, get something like this. And that means my resultant vector, u plus w, should be that. Y'all still good with that? And what about v plus u plus w? What could I do for that? Anyone have a clever way I could do that real quick? Yeah, why don't we take this w and just add it to this? Right? V plus u we already did. So if we want to add w to it, all I want to do is take this red one, move it up, over, attach it to the tip of v plus u. So put it about right there, and then draw it out like this. So that's your w right there. And then start it here, up to there. That's that one, right? Does it matter the order? No, remember. Oh, with subtracting. What's your gut tell you?
Well, if it follows the rule,
Yeah, subtraction does matter. Subtraction does matter, the order. Yeah, it's going to do something. Let's talk about it. We are going to get to it when we talk about first. This is the vector addition. I showed you visually, right, what's happening, but how do you mechanically add two vectors together? And it's very straightforward. If I have two vectors, u and v, So I'm calling the vector u, it has components u1, u2, and the vector v components v1, v2. Then if I want to add the two vectors together, all you do is add the components. So you add their x components together, u1 and v1, comma, then you add their y components together, and that result is the resultant vector.
And that will give you an equivalent vector.
That'll give you that one that we were coming up with, yep. It's not equivalent to both of them. It's equivalent to the one where you tail tip, that resultant. All right, so same thing with R3. Let's just do an example. Maybe not. I thought I had an example here. I don't. I think it's coming. All right, scalar multiplication. Now, I think this is a good time to stop and just think about something. When we were learning numbers, right, in our life, we learned about numbers. We learned addition first, right, and then probably subtraction, and then we learned multiplication, and we learned division. When we learned multiplication, you could take any number, multiply it times any other number, right? And you would get some result, 8 here, right? When we're saying scalar multiplication, what we're saying is what happens when you take a vector and multiply it times a number, real number. See, that is not the same. The reason I was saying when you learned multiplication is because when you've multiplied in your past, it's always been number times number, right? And we have a very clear idea of what number times number means. But what happens when you take number times vector? And even more than that, what does vector times vector mean? Right? We know what vector plus vector means, but what's vector times vector? We're not ready for that yet. It's actually the title of this section. The section is called dot product. Okay? We'll get to it. Right now, we're not doing vector times vector. We're doing number times vector. Real number times vector. And all this real number times a vector is a stretching out of the vector, a scaling of the vector. Almost like, you know, in pre-cal, you had the a in front of the sine function or cosine when your amplitude would like stretch it out, right? That's all this does. It stretches out our vector. So if we have some number c in front of our vector, then c changes the shape. If the absolute value of c is bigger than 1, it stretches it, makes it longer. If the absolute value of c is between 0 and 1, it will shrink it, make it smaller. If c is negative, it flips the vector and points it into the other direction. Also, when you're actually doing the computation of multiplying a scalar times a vector, the scalar just passes through to each component, almost like a distribution through the components of the vector. Same thing in three-dimensional space. So let's take a look at it. The picture here is the vector. You can see this vector v. I'm sorry, these are on top of each other. But there's the vector v. Right now I'm scaling it by 1. If I scale it by 2, it's twice as long, right? So here's the vector v. If I scale it by 2, it's twice as long. Now what if I change the direction of v? Or its length? So if I make v smaller, that 2v is still twice as long, right? As I change the direction, 2 times v, it changes direction also, right? So scalar multiplication of a vector does not have any impact on its direction. It's just the length. Now what if I multiply it by a negative number? It's going to point it in the opposite direction. So v is still pointed this way. Negative 1.25v is pointed this way, and it's a little bit longer than v was, right? And what if c is 0? What do you get? You get the 0 vector. You don't get 0, right? You get the 0 vector. And I wonder what will happen if I put 0 in here. Yeah, my code wasn't ready for that. But look, it spit it out right here. Okay? 0, 0. All right, moving along.
So no matter where you move the vector, it's always gonna, the number's always gonna stay the same.
What number?
The C value.
No matter where.
Like let's say you change the size of the vector.
Well, that's just the way I wrote this program.
Oh, okay.
I just wrote it so that if I chose to change V, it's always going to draw 1.25 V here. All right, now the parallel. Let's talk about this again. Any two vectors are said to be parallel if they are scalar multiples of one another. Now, we just said that what scalar multiplication was, right? So here's what this is saying. U, the vector U, is parallel to the vector V. So I have two vectors, right? The only way that they will be parallel is this. If U is equal to some scalar multiple of V.
Is it just like, can it be the other way around? Like if you multiply U times a C
Yes.
to B?
Mm-hmm. If you want to still use this, just look at it this way. 1 over C times U is equal to V. So V is some scalar multiple of U, right? Either way, it doesn't matter which way you do it. So let me give you an example. Let's say U is 8 and I don't know. We'll make this really, really simple. 8, 2. And V is 4, 1. Are these vectors parallel?
Yeah.
Yes. And you can tell because how could you get U from V? Just double this one, right? If I take this and I go 2 times V would be, what, 2 times 4 and then 2 times 1. Of course, that would be 8, 2, and that's this, right? Now, I also heard you could also do this. 1/2 of U is what? What's half of U?
V.
Is 4, 1, right? Which is V. So they're scalar multiples of one another. Yeah?
If C is -1, would that still be?
Okay, yeah, so now that was what I wanted to do next. How about these two vectors? Let's go, U is -8, -2, and V is 4, 1. Are these parallel?
Yes.
Yes, they are parallel because they are scalar multiples of one another, right? U is actually -2 V, isn't it?
Yes.
And that's what it means to be a scalar multiple. Are these pointed in the same direction?
No.
No, they are not. They're pointed in opposite directions. How do you know they're pointed in opposite directions? We just said that if you take a vector V and you multiply it by a negative, it points it in the opposite direction, right? So we're taking V, we're multiplying it by a negative, which points it in the opposite direction, and we're doubling its length. So when you graph these two, they lie on the same line, but they don't point in the same direction, but they're still parallel. Okay? So that's kind of weird that the idea of parallel with vectors, the direction can be opposite and they're still parallel. Questions? All right, now the next idea is the magnitude of a vector. So how do we find the magnitude of a vector? This is just a formula. You can get it by using Pythagorean. A squared plus b squared is c squared. Just draw a picture. So I won't go through it. But we do have some notation and some language. The magnitude or the length of a vector in R2 is notated with the absolute value bars. Okay, that you've grown up with, you know those. If you throw absolute value bars around the vector, then what you need to do is take the square root of the sum of the squares of the components. So you're just going to square the v1, square the v2, add them together, take the square root. Now, if your vector is in three-dimensional space and you've got the three components, then you'll square each of the three components, add them all together, take the square root. That's also the length of v. Does it make sense to you that those formulas would be those? Yeah? Okay.
And that's for, I'm confused what is that for?
How long the vectors. That gives us if we ever need to measure the length of our vector, which we will, that's how we can get it. All right? How much of this do I want to do? Let's just do this example, just parts C and D. And why don't I let you do parts C and D? We won't do much like group work in this class, but just to give you a little break here, working very quickly and working together if you'd like, see how fast you can knock out C and D. You need to figure out can y'all read it? I'll zoom in a little bit here. I give you two vectors, v and u. I ask you to find 4v minus 3u. Give me that vector in angled brackets. And then, after that, give me the length of that vector. Sound good? All right. Enjoy.